I wonder why. It's a PDF, but
Well, I know they have a digital scaler on here to try to make sure that everything displays properly, but maybe that's part of it.
okay.
Okay, I think we're up and good to go.
Okay, let's get started. Welcome to our weather discussion, everybody, especially alumni, Rusty and Dave, maybe others. I haven't had a chance to shake any hands. I had to come back from another event right before this. I've just got a couple of things I want to talk about today. One is the evolving cold pool over the Northern Hemisphere for a minute, because I've been away last week, and then I didn't bring it up the week before, so we've had like 2 weeks of transpiration since then. It's kind of an interesting 2 weeks, as it turns out. And then I want to look at a storm that was in the North Pacific over the week, which was really interesting. And then we'll talk about our current weather over the continent, and because it really needs to be discussed. It's so incredibly warm outside after a week of really record cold in a lot of places. And we stand to make a run at tying the all-time record for the last 80-degree day of the calendar year, which is Sunday the 23rd, and that's the last time it was 80, was October 23rd, 1963 is the latest 80-degree day in Madison's history. So we'll talk a little bit about all of that stuff. Okay, but let me start with the cold pool. First, this is the time series for this year, from September 1 through October 20th, so not today. And then you can see several averages, 51 to 80 averages in black, 48 to 2014 average, the overall averages in blue, and then the most recent climatological average, which, well, actually, maybe it should have been updated 1990 to 2021, or 91 to 20. Anyway, you can see they don't vary very much in terms of how fast the cold air builds up over the Northern Hemisphere all the way to the end of December. And it's not quite at a peak there. But here's the time series. For a while, we were a little well below the average in the early part of September, and then we were kind of right along the average to the end of that month. And then we flatlined at 30 million square kilometers. And these 3 yellow dots indicate that without checking the last couple of years, this would have been all the way through 2019 now. These are the 3 warmest October 18th, 19th, and 20th by this measure ever in the 75-year time series. So that's noteworthy. I can't think of another time where I've seen 3 straight days merit that distinction. So that's kind of interesting. And yet, this was a period here where we were, waking up to 29 degrees, 32 degrees, and 34 degrees. And driving home on the bus on Tuesday, 45 degrees. I had my wool jacket on Monday and Tuesday this week. I've never done that in October before, ever. Pretty unbelievable, okay? So that is really very interesting. And despite this flatlining, which puts us way below the date average, we're still only the 14th warmest September 1st through October 20th in the 75-year time series. I thought for sure when I saw that, I was going to get somewhere in the top 5 or something. Nope. So I think in some ways the die is cast by September. It just seems like you got to have something extraordinary happen the rest of the run up to December 1 for it to really knock you out of whatever rank you achieve by about early October. So that might be wrong, but this is interesting. We've kind of flatlined in the hemisphere. Let me show you another chart. We can get rid of this one. And that's 6Z on Tuesday. So midnight Monday into Tuesday morning. Let me explain what's on here. First, the green dashed line is the average position of the -5 isotherm at 850 around the hemisphere for that exact synoptic time, 6Z on the 18th of October. Then the Dr. Pepper colored line is the actual -5 degree isotherm at that time. And then we've got standard deviation. So surrounding the average, everything in white is +1/2 standard deviation or -1/2 standard deviation, depending on which way you go. Then it's 1 to 2 in the light blue, 2 to 3. 1 to 2, 2 to 3, and then 3 to 4 in the dark blue. And look what was true here, like in Nashville. It was almost a 4 standard deviation below normal temperature at 850 that morning. And then that column of really chilly air all the way from the archipelago straight through Wisconsin made its way down to the southeast. And this was what people were talking about unusually early frost and freeze warnings in places to the south. And yet, when you look at the hemispheric picture, there's a whole bunch of these tendrils. This is the one that penetrates farthest south, but there's one over the British Isles, or Scandinavia, I should say. There's one here over central Russia. There's one that kind of gets over to the Kamchatka Peninsula in northern Japan, and then a little bit of a sprig that heads southward from where? Right about the dateline, central part of the Bering Sea, where the snow crab have disappeared. 90% of the snow crabs are gone. What's going on there? And they're insects, right? So, I mean, it's kind of scary. But look at, if you do kind of a by eye calculation, every place where the actual -5 isotherm is poleward of the average, this is a region that is much warmer than normal. So the much warmer than normal regions far exceed those that are colder than normal in the area. So the whole day, even though we were really cold here, is a lot warmer than normal around the hemisphere by this measure. So that kind of explains the flatlining that's going on. And so I like this depiction for a lot of reasons, but one of them is this. It really helps a person disentangle the notion that climate and weather are really very strongly almost the same thing. They're not the same thing. I mean, the climatological perspective on this is that we have a very warm October 18th, but not true regionally. And you can see that all of that's verified in one quick glance. So I guess I meant to say regional weather and climate are correlated. They're not. They're not in any systematic way from one day to the next at random. So that's pretty cool. Okay, so stay tuned. I'm always hoping for hardware. I want to see the warmest ever September to December 1st. That won't happen. And then I want to see the warmest ever winter, December, January, February, because we're never going to get the coldest. We don't even get 2 sigma cold days anymore. They haven't happened since 1994. So that's completely out of the question, but I'd love to get the warmest one. But I have no idea whether that's going to happen. But I like hardware. So, okay, Pete, let's, the next thing I'd like to do is, I'll mention this. I think I might have already done it. October 23rd, 1963 is the latest day that Madison's ever recorded 80 degrees Fahrenheit. So when we get to the forecast, we'll be looking at how close we might make a run at that. And it will be on the same calendar day. Sunday will be the 23rd this year. So somewhat unexpectedly, we get this really big warm surge. What was interesting discussing this yesterday in class, Jake and Aaron did this, is we had, I think maybe Isaac even asked the question, or maybe it's Kalen, you said, how come it's getting warmer as the weekend goes on? What's the temperature advection look like? And it was southwesterly flow or northwesterly flow, warm advection. And so I want to see if that's the case today. So that was really kind of an interesting thermal structure connected to the kinematic structure that you want to interrogate. So let's take a look at the current weather, and then I want to go back to the Pacific earlier in the week for a minute. This is, it's now Hurricane Rosalind. It's still tropical storm, so maybe it's going to be a hurricane. I don't know, maybe time's running out on Roswell. Maybe it's not going to quite get there. I think the forecast yesterday was for a hurricane category 2, but just as it made landfall, but I thought it was already supposed to be a hurricane by now. But anyway, tropics in the eastern Pacific anyway continue to churn away, and this is an interesting looking storm. Watch right here. There's a blowout and then an expansion of that one convective tower around the eye. You can kind of see that. That's really nice. And really nice weather in the central part of the United States. One can almost see the ridginess over the Great Lakes in this bit of the cloud mass over the Ohio River Valley, but maybe that's a bit of an imagination on my part. Crystal clear and yesterday in the Pacific Northwest. Now that cyclone that was out in the Pacific has kind of made landfall, so the clouds have repopulated the sky, but you can see the offshore flow over Northern California and the complete lack of stratus clouds there as a consequence. Probably as a consequence, I should say. I don't know that's for sure the case. And we had a lot of lake effect cloudiness over the northeastern United States yesterday. Some of it was even precipitating in Pennsylvania, New York. That's all gone away because it's now, the colder air has moved farther south and there's been some moderation of it. And that's made a difference, I'm guessing. Okay, let's take a look quickly at the radar across the country.
Is that smoke that we're seeing where it's kind of gray? I know there was some
Right
big
in here?
fires. Yeah, and even into like Illinois, Indiana, Ohio,
There's
some
a
of that's
fire.
It is fire?
There's a fire in the Pacific Northwest.
a big fire
Okay.
in north of Portland, I think, or east of Portland.
Oh, is that right?
Yeah.
Wow. So these clouds might be a good thing for that if it's raining on them. We'll see in a minute in the radar. So
Anyways,
that's a widespread
That looks
smoke
more
plume.
smoky than just like brown dirt or anything.
Yeah, it sure does. Yeah, it sure does. That's amazing. I mean, this is such great imagery to be able to see that, and we saw it all through September. You know, one after another. It was really neat. Let's take a look at the Pacific satellite first before we look at the radar. Okay, so the Pacific Basin is a little bit less interesting than it was a couple of days ago, but we have a couple of interesting features nonetheless. One is this cloud streak that goes all the way from the dateline at about 45 degrees north latitude all the way to Oregon and Washington. That is interesting. We'll see what that looks like in terms of its depiction in the jet stream and various other variables at the same time. One thing you can see almost immediately is that to the south side of this feature, which presumably is tied to the jet and therefore tied to some variochronicity, is an absence of any convective-looking clouds. And then up in the Gulf of Alaska, where presumably it's colder on the poleward side of that jet, you've got open cellular convection. And some of it's even trying to organize, it looks like, although finding it difficult to do so. We might see why when we look at the actual observations of the upper level winds. But then, just to the northwest of Hawaii, there's this really interesting tropical upper tropospheric trough that's kind of sitting there, and all of this looks convective and a really nice rotation going on there. I think I know where this came from. This came from that big event that was 2 days ago, that the discussion in 452 mentioned at the beginning. I think Kaylin were talking about that really beautiful cyclone here. That's what I've got on VisMarGeek today, to look at that thing. And so when you'll see, when it gets all wrapped up, it kind of drops this little dollop of high PV down here, and that's the feature. And it takes a long time for these things to go away. I was on a plane last weekend on the way home from Philadelphia, and where did we land somewhere? It wasn't nonstop, but anyway, it was kind of low clouds and fog, and you can see the wingtip vortices on the end of the wings. It's really fun to watch them. And they're proof positive that vorticity is really hard to get rid of. It's not easy to just get rid of it. And this is a large-scale example of that. And then the ITCZ, Anita Rapp's talk was so interesting to me on Monday. I hope you got to see it. Calculating the area in which there's updrafts. Seems like such a simple idea, but what a powerful set of insights came from that. And so you can see that there's big gaps in the ITCZ today in this part of the hemisphere, and then maybe some others further to the west. Sometimes it's lit up like a Christmas tree, and other times it looks like a first grader's teeth, like it does today. So I don't know how to describe it better than that. Okay, thanks, Pete. Now, can we go to the radar? Let's take a look at the radar across the central U.S. So here's where it's raining. So this might be good news for the fires if they are indeed north of Portland. They're probably getting a little bit damp, which is good, and that thing seems to be making progress to the south and east, which furthers the good news for them. But look at how widespread the lack of precipitation across the United States is. I'd say 4/5, 5/6 of the country without any precipitation. Here's something in the northern Baja, which maybe is tied to Rosalind's cloud shield, or maybe it's kind of independently but weakly associated with it. Down there, I don't think there's anything really meteorologically interesting in the panhandle area of Texas. That might be some weird artifact of somebody turning the radar up and down. I don't know. Maybe we'll see in the ops. So that's the precipitation event over the continental U.S. right now. Little bit of maybe lake effect reflectivity here. Maybe it's not even reaching the ground, but some hygromedias are being picked up on the radar at Marquette. And then the Imperial Valley seems to have something going on, but that might just be fog, actually, too. They might have turned them on high for fog today. Okay, so let's go to some upper level charts to get a diagnosis of the current time. And we use the super Petes for alumni. Pete Pokrant's been worth his weight times 10 in gold to this department over a long period of time. And every chance I get to say that, I like to say it because I mean it. And so we call these big, almost hemispheric maps the super Petes, because Pete puts them together and they're super big. So that's what we call them. So here's the 500 millibar map from 7 a.m. this morning. Troughiness over the southeastern United States. We saw just a hint of a little bit of precipitation off the Carolina coast, just outside the radar range. I think we also, you might recall, we saw a cloud shield well offshore, perhaps in association in the southern end with this curvature region, and then maybe over the New England and maritime Canada latitudes from the confluence that's going on here. And on the warm side of that confluence, you'll have some ascent. So that's probably what pickles that together. And then deep upper level trough over the northeastern part of Hudson Bay. That's the feature that's kind of controlled our weather over the last several days until the last one or two. And then we've got this broad northwesterly flow, which is strongly baroclinic. It's minus 31 here at Juneau. And then this isotherm here is the minus 10 isotherm. So this is it minus 10? Maybe it's minus 15. No, it's minus 10. So that's a pretty strong upper baroclinic zone in northwesterly flow. The exact nature of the flow and the strength of the gradient is probably fairly unresolved, except by prior forecast models. There's no odds there. Boy, is that a sensitive region. If you can get, like right in here, you've got cold advection going on, as the analysis suggests, in a region of cyclonic shear. That means the air is sinking on the warm side of that baroclinic zone, dragging the tropopause down. And so that's the genesis region for a next upper level vortex feature. And so that feature is going to come roaring into the northern United States. I think, we don't know exactly how it's going to go, except our models are so good today. we'll keep that in mind for the forecast, but that's going to be a feature of some interest. And then the sort of cutoff off the southwest coast of the United States, almost perfectly climatological feature at this time of year, as it turns out. And that often induces offshore flow, Santa Ana type flow. Doesn't seem like that's all put together the right way this time, and that's good news. We had Santa Ana from late August until end of September, so we don't need it again, even though this is when it usually shows up. So at 500 millibars in our region, there's really no evidence at all of any temperature advection. It's minus 12 in Bismarck, minus 14 at Pierre, minus 14 in Minneapolis, minus 14 in Green Bay. So there's just zero, almost zero temperature advection at 500 millibars. Let's see what it looks like though at, we'll go down first. Let's go down to 700 P. So here's the 700 millibar analysis at the same time. And you start to see, there's a little bit more evidence of temperature advection at 700 in the same location. It's colder to the northwest in southern Canada, Saskatchewan, Alberta, and then warmer over us. We're +4 at Green Bay, +4 at Minneapolis, generally +4 in this region, but a little bit colder to the north and west. And you can see the cold advection in association with the northwesterly flow, especially right offshore of British Columbia and Washington, is a little bit more intense than it looked at 500 millibars, though maybe roughly the same. How about 850? And at 850, kind of looks entirely different. We're in a little warm bubble. Here's an axis of warm air, coincident with the geopotential height minimum. So that's like a lee side trough. I'm guessing. We could trace it and see whether that's true, but I think it is true with the preponderance of kind of westerly, northwesterly flow over the high terrain, which is oriented like this. That's a lee side warm bubble. And we are the beneficiaries of it at 850 because the warmest air is to our southwest, and we are to the east of the trough axis, so we have strong southwesterly flow, and that's warm air advection. So the warmest it could possibly get, and it won't get to +20 at 850 for us. It's only at +11 at Green Bay, maybe it's +11 at Madison. It won't get anywhere near +20, but if it did, 80 would be in the bag. So that's going to slip south of us, it looks like. And then, right there is this is such a nice structure. Coincident axis of geopotential height minimum, axis of warmest air, which means just to its west, it's going to be cold advection. And so that's the next thing for us to worry about, although it's not horribly cold, but it is cold, no doubt. So kind of interesting setup for us, and we'll go back to this when we look at the forecast and try and put those pieces together. So the next thing I wanted to talk about, Pete, is let's go to Alicia Bentley's GFS maps first, and then we'll take a look at the broad complexion of this event that occurred over the Pacific Ocean earlier this week. So the 16th was last Sunday, right? So this is Saturday night, and here's a little cyclone in the sea level isobars are in black every 4 millibars, 1,000 to 500 thickness is red until you get to 540, then it's blue, and then the shading is the 250 millibar wind speeds. And so you can see here's a jet streak that was sitting there on Sunday night, and a weak cyclone, 1,004 millibars maybe at its central pressure, but with a decent baroclinicity through the deep column because it's 1,000 to 500 thickness. It's not just one level. That's a deep baroclinic zone, and it's sitting right here in the sort of what I guess you'd call it the right entrance region of the jet. So there's something positive about being a cyclone in that spot. You're going to have a tendency for ascent. The jet's also anisoconically curved, so there'll be a little bit of supergeostrophy through there. So there's even more ageostrophic divergence than you might get just from the speed change. That's a good place to be if you're trying to develop something out of nothing. And yet, we're going to watch this evolve. The cyclone is going to move across the jet axis and then get into the right exit region of the jet, left exit region, I don't know my left or my right, sorry. The left exit region of the jet, and that's a really good place as well for development. So for a period of time, this cyclone develops south of the jet, then it goes through a short period of stasis where it doesn't do much development, finds itself polar to the jet axis, and boom, it goes wild. So let's click through this, Pete, one at a time, just to kind of keep track of that. So here's our cyclone, this is 1,008, so now we're down to 1,000 millibars, kind of at the center of the jet streak. It's still anisoconically curved. We haven't gone below 1,000 yet, maybe 996. 996, and now maybe, what is this, 840, that's 992. And now we're getting close to the other side of the jet axis, and watch what happens. That's 1,006 to 988. One more time. Boom, here we go. Big development. And look where the cyclone is relative to the jet axis. It's now getting closer to that left exit region, and we can keep going. And this is a really quite dramatic development. 992 is which one? Gee, I'm going to count this for you because it's so interesting. 1, 2, 3, 4, 5, 6, 7, 8 times. That's 978 in the middle there. Even lower at the next time. And notice, we go back to that prior time, Pete, because it shows the thermal structure so nicely. Posh gave a really nice talk on occluded structures on Wednesday. And look at this thickness field. It would show up in our identification, Posh. It would definitely do so. There is a local maximum thermal ridge. But when you look at this thing in more detail, we'll do that in a minute, you find out that it really doesn't have the most robust occluded structure because, I have a feeling, it's because this whole flow is too high amplitude and it never really allows this thing to cut off. It just is very progressive on its eastern side. So I'll show you that from Vis 5D perspective in just a minute. So it's a nice intense cyclone, and I wish we had a satellite picture because the satellite depiction of this was beautiful. Really racked up clouds in the center of that storm. I think this is about the time we were talking about it too, Tuesday. And then a really nice trailing cold front associated with it. Meanwhile, upstream, there's another intense disturbance getting organized over Kamchatka. That has a more obviously well-developed occluded structure, as it turns out. So let's go back one more time, Pete. Click all the way back to that beginning time, 0Z on the 16th. And there we are. So there's, all you have really is pretty much a zonal jet with a couple of humps in it. It's strongly baroclinic. You can see the thickness gradient is paying attention to the jet and vice versa. There's no particular tropical influence on the development of these. And so something happens where both of these little blips in the jet really develop. So let's click again and just watch that develop. Both the cyclone of interest and the one to the west. So a really explosive development. So this thing presented itself beautifully in the satellite by the time we got to Tuesday. Okay? But a really intriguing thermal structure. Very intense baroclinic zone right back here. Very intense cold front. Stubby little warm front. And then this gap that actually does qualify as a thermal ridge, but it doesn't really look occluded when you cut it in a number of different ways. I won't spend all those times doing it. So Posh, if we'd been looking at this one in our, getting our hands dirty with the data, we probably would have said, yeah, it works, I guess. We'll hope that it averages out if it's got weird structures. Because we wouldn't throw it out, but we wouldn't really feel great about it. It's a weird one. Okay? The one to the west would be much better. Okay, so that's what I want to talk about is, how did this storm begin to develop south of the jet? What happened when it got across the jet on the northern side of it, and what were the developmental mechanisms there? And that'll be the end of that part of the discussion. So if we can go to Vis 5D, Pete, that would be great. So this is 0Z Sunday, so this is October 16th, and we're looking at sea level pressure. And if we can put the speed on there, the isosurface of speed. That's okay, that's okay. I have an isosurface, I don't know why it doesn't show up. Oh, do you have to hit okay again for these? I think you do. Okay, so there's the 50 meter per second isotac, and this is a good one to put on too. That's helpful for you, actually. So I got that ready. And for the time being, let's take the red off just for now, because you can't see through it so well. So here are the isotacs at 12 kilometers, so it's right about at the tropopause level in the yellow, and then here's the sea level pressure minimum associated with the storm of interest. And so you can see it's kind of located just as it was on the GFS, because this is the GFS, but just in Vis 5D format, near the right jet entrance region and of an anicyclonically curved jet. And there's the cyclone minimum. When the pressures get below 1,000 millibars, so 996, 992, I turn them into blue, so you can watch how that thing develops and when it develops as we click forward. So let's go forward again. So we're still at 1,004, 1,000. Takes a long time. There's finally 996, and that's on Monday at 0Z. A whole day's gone by, and we're still south of the jet core. So let's keep going. And then 992 barely squeaks in by the end of the day, middle of the day, Monday, and then it really starts to go wild. So you can see these new blue isobars sprouting up out of the ground as the storm gets more and more intense. And then notice that it's located in the right exit region of the jet, broadly speaking. And let's go back a couple of times, Pete, and put the colored speed on there. So yeah, so there you can see a really nice relationship between the isotac maximum in 3D and the position of the cyclone. And there's even this little one here that's contributing in the same way, but for a different reason, to the development. So it's really nice. And then, I'm not gonna say much about the storm upstream, but it has the same kind of relationship. Okay, so that's really interesting. Let's do one other thing now. We can go back to the initial time. We'll take all of these things off, and we'll just look at the PV. It's a 2 PVU surface. Yeah, okay, great, okay. So here's the 2 PVU surface. It's like the tropopause. We can tilt around and see what the colors mean. They're pressure coded, so the higher pressures, so lower elevations of the tropopause are in yellow, and then the blues are higher elevations, lower pressures. So you can kind of see the corrugation of the tropopause here. And if we slide it back down to a view, maybe slide around a little bit too, Pete, so we can kind of get it in, look at a view from the east as you're spinning it. Yeah, perfect. So, and then drag this down. So you can see how steep that boundary is. And that's going to be the spot where this tropopause PV gradient is largest, and that's where the jet will be. So if we put the jet on top, the speed ice attacks, look at that. They cling to those regions of really strong tropopause slope. Okay, so that's something that's always going on in the vicinity of a steeply sloped tropopause. And this is the one that's tied to our development of interest. Okay, so that's kind of interesting. Then let's get rid of the PV, because I think it's interesting, but it's not the main story today. And then put the mean sea level pressure on again, Pete. And then, let's see, let's put, I forget what level I had theta at. Let's see what it tells me. Yeah, 7.5 kilometers. Okay, so that's pretty high up. This is potential temperature now in purple. And you can see it in the, like at 400 millibars or so, there's a really decent horizontal temperature contrast just poleward of the cyclone. Remember, the cyclone was also tied to the jet there, so that's not surprising. Now we can calculate the frontogenesis along that baroclinic zone, and that's at the same level. And so here we see a little bit of horizontal frontogenesis going on along these baroclinic zones. It's not particularly well organized at this time. Let's click forward though. This thing looks coherent, and it's coming in into the vicinity of the struggling cyclone. It's got a little water in the carburetor until now, 996. So this feature of horizontal frontogenesis has migrated along this baroclinic zone in northwesterly flow, changed its orientation, and found itself in a really nice position relative to the cyclone setup by this time, which is 03Z Monday. Let's take a vertical cross-section of that variable, Pete. Yeah, we're going to have to move it, so we want to slide it to right about here, if you can do that. We can get the middle point.
Well, just grab the...
Yeah, it's not easy to tell where it is, but when you get it, it works. Perfect, that's really good. So it's cutting the baroclinic zone at a nice angle, and it's cutting right through one of the maxima in frontogenesis. So let's see what it looks like in the vertical. Where is this frontogenesis occurring? I think that's the upside down vertical. Isn't it?
You're just looking at it from the west.
Oh, yeah, okay, all right. Sorry, Pete.
So here's the top. Do you want to look at it from the east or the
I'm
west?
gonna look at it from the southwest. Yeah, thanks, great. Okay, so here's that feature. Down in the, let's put theta E on here too. I think I have theta E. Up, down, yeah, right there. That's right.
It's probably in a different place.
I might have another one down here. I think I made a second variable of theta E. Yeah, I did. Okay. And then that one started out in the same place. So just, if you make it coincident, that'll be useful. Thanks. Okay, so we're interrogating what's going on here with this baroclinic zone, and we're going to look at theta E and frontogenesis. Wow, this is a pretty intense zone of moisture and temperature contrast. It goes all the way up to 9 or 10 kilometers, and it's strongly frontogenetical in the upper troposphere, and seems to be fairly strongly frontogenetical in the lower troposphere. Very often, I won't show it today, very often that's a function of just convergence near the ground. So that's going to help to assist creating a vertical motion plume. Let's now put the vertical motion on top here. And I think it was this one here. We might have to move that too. So we got forcing for the horizontal winds. The frontogenesis function is telling us the horizontal winds are impacting the temperature contrast. There's going to be an updraft that's forced on the warm side when that happens. And look at that. There's the updraft. right in there. Beautiful. And if you can tilt down just a little bit, Pete, oh yeah, that's right over the cyclone minimum seal of pressure. So we've got this, when you go back to the plan view aloft, we've got this middle and upper tropospheric baroclinic zone that's frontogenetically active. So this is positive horizontal frontogenesis. Warm air will rise, cold air will sink. The warm air that's rising is poorly stratified. You can see that in the theta E cross-section. So it zooms upward in the face of this forcing, and that's the air that's evacuated out of the center of the cyclone. So for a while, this storm is developing, this is my conjecture today, this storm is developing because of the middle and upper tropospheric frontogenetic activity, not really because of anything else. And remember where the jet was here, if we can put the speed isotachs on there. Yeah, so this is frontogenetic activity right through the core of the jet, and the ascent's going up, taking mass out of the column. So let's go forward a couple of times without the speed on there, Pete. And look at how it hangs together with that. Go one time back. Look at that. Really nice baroclinic zone and frontogenetic activity along it. Cyclone's getting more intense. If we can slide these cross sections to about there, we'll see what the relationship looks like. Let's do one at a time, so we'll just look at the frontogenesis first, and then we'll do the same kind of orientation. So here's what the frontogenesis looks like at this time. This is the same piece we saw before, but it's kind of been supplanted by a little bit deeper thing in the lower troposphere. See what theta E looks like there. Right along the front edge of that baroclinic zone. This one's along the front edge of another one. And what about the plume of vertical motion? Right in there. And the cyclone center is right here. If we tilt it down just a fraction, you can see that. There's the cyclone center, there's the updraft right on top. So this is, we were just talking about this in 452, and you know I'm excited about that variable because it's so powerful. You can use it to do a lot of diagnosis of the way things are working in the weather system. Okay, let's go back to the top, Pete, and let's click forward a few more times when the storm's really starting to develop. Now it's going to traverse the jet, right there is good, and then maybe we want to take a cross-section like that. Oh yeah, I'm in your way too. That doesn't help. Yeah, perfect. I'm gonna stay in the shadows, literally.
That's okay, I can see it on the monitor here too.
Okay, and we'll do the same thing. We'll start with just the frontogenesis function. Now we're on the right entrance region of the jet. So the frontogenetic activity is over here. Let's see what this looks like. Much deeper. Look at that. Look at how deep that upper tropospheric piece is now. This stuff here is a little bit more intense in the lower troposphere, but this one's really much more intense and more expansive. And then theta E, same basic structure. You get this really intense baroclinic zone here that's frontogenetically active in the middle troposphere, and then the vertical motion. Look at that. Strong updraft. There's another one over here, but this is the one that's fueling the cyclogenesis, it looks like to me, because it's right over the minimum in sea level pressure. So it's just a fantastic, I guess this is just an initial analysis into what's really driving this development, but it's pretty interesting. And then I think, I won't say any more about it now, but you can see when you look at the geopotential height contours at upper levels, and finally it does develop a really intense curvature maximum, and so then you've got a nice local vorticity maximum. We can see that from the PV if we go back to the PV and take everything else off. Well, we'll put the sea level pressure back on, and we'll drag it all the way to the top. I think it is at the top. Yeah, leave them both on there. Are they both at the high level?
No.
So let's drag that one up to the height too. And then make sure that one is, I think it is.
It is.
Oh, it is, okay, great. So let's take a look at this. Okay, let's go back to the beginning. Okay, so here's our initial condition. Remember, here's the steep tropopause. The jet was there. Remember, there's the anisotronically curved jet. Let's just page through this. And you can kind of tell where the jet's going to be. And then look at how this tropopause trench is being dug back here in the subsidence side of that upper frontogenesis. We were thinking about the ascent side for the development, but there's subsidence going on too that drags the tropopause down. And so here it comes. And watch this. This is so awesome. That's the main feature for the southern storm. This thing, look at that. It gets this really intense little curve. Take the sea level pressure off just for a second. Look at that little curlicue. That's what we saw in the satellite. And then there's this little dollop of PV. Let's animate this all by itself, Pete. So here we go. Development, main cyclone, little dollop. And that's the thing that's still sitting out there. That's got all the convection there. So it's all tied to this development. And they take a long time to go away. But this is how the high latitudes drip circulation away. Eventually it does go away, and that little bit of circulation never comes back. So it's a drip that goes away. And there it is, from another view. So pretty cool, isn't it? So that's a pretty cool evolution that we saw this week. And this is such a great tool to be able to do it. And Pete, you drive expertly. And there's 996 and below was the blue. And look at that little cyclone that develops down there. Right here. There's the sea level pressure minimum. Isn't that awesome? Okay, we have to say something about the forecast too, because man, it's going to be wild this weekend in terms of warmth. So let's take a look at the current ops first at the surface. Just how widespread and how extreme is this warmth over our region. So we're at 68, unbelievable. It was just 62 an hour ago, so that's a 6-degree increase.
Why I can't slide that through.
Snowing in Alaska, that's neat. Yeah, it makes you use the scroll bars. doesn't it?
Yeah.
So 68 over 37, it's 69 in Milwaukee, it's 74 in St. Louis. There are widespread 78 in Waterloo, there's 70s in a large chunk of the central United States. And even up near the colder lakes, it's in the high 50s. I don't think they expect the weather to be so nice in late October like that. 68 over 37, incredible. Okay, so we already saw at 8:50 that there's kind of modest warm advection ahead of what I think is the residual lee side warm bubble. We want to see what it looks like as we go into the weekend. So let's go to Pete, to your GFS maps, and we'll particularly start at 8:50. So we'll look at where are we now in 0 hour, 3 hours. So this is 12Z this morning, and so there's a nice colored depiction of our warm bubble. That's a lee side trough. The coincidence of the highest temperature and the geopotential trough is a really nice indication of that. And you can see at a glance, geostrophic warm advection is fairly intense here in southern Wisconsin. So that's at 12Z. Let's see what it looks like now, 6 hours into the future. We ought to be closer to the axis of the maximum in that warm tongue. Actually, we're not going to see any more warm advection. We're probably going to top out at 68, 70 today. That's it. But then there'll be a cold advection back behind it, presumably. Let's see how that goes in the future. So maybe every 6 or 12 hours. So this, actually, I'll take it back. There's still a little bit of warm advection by nighttime tonight, so it's going to have a hard time cooling down. And this warm bubble is just resisting moving. We're going to have to, in a minute, just examine what might be underlying that. But this is continued warm advection for us by midnight tonight, so I take it all back. The baroclinicity has stubbornly remained to the north and west. Can we go back a couple of times, Pete? I wasn't paying attention enough. Maybe we'll go back to the 6 hour forecast. Here comes a little troughlет in the flow, and that might be the feature that we were talking about at 500 millibars, or at least responding to it. Most likely a number of vorticity features developing along the British Columbia coast. Downstream of it, in combination with the flow over the high terrain, there's a new disturbance that's going to develop. And the warm advection out ahead of this feature is kind of pushing the cold air back to the north over Minnesota instead of letting it rush in over us. That might be what's going on. So let's go to the next 6 hour time.
24.
Yeah. So here's a better developed cyclone in association presumably with that feature. And then it has a broad region of low geopotential height and then warm advection over southeast or southwestern Minnesota that keeps that baroclinicity away from us. That might be the thing that keeps us unusually warm overnight, gives us a good start for even high temperature tomorrow. If that persists on Sunday, I don't know. All right, let's go a little further ahead. Wow, these temperatures are really high. That is plus 24, 22, 20, plus 20. That's like 68 degrees at 850. And it's going to be breezy. As you can see, the geopotential height contours are close together. There's not really any particularly strong warm advection. Maybe there's zero advection, but there could be mixing. And if you drop one of those 20 degree C parcels down 1.5 kilometers, it'll be 9 degrees warmer. So we're going to be close. And this is midday Saturday. Persistent warmth over the Central Plains. It must be because of can we just take a sojourn to like 500 millibars, or maybe 300 is even better at the same time. Yeah, it's surprising. I thought I would see stronger across mountain flow. The mountains are about like that. It's pretty strong, I guess. That's pretty strong across mountain flow, keeping it warm in the high plains. Not sure why it's staying so warm over Nebraska and Kansas. Maybe it's just taking a long time to get out of it. But there is a tendency for adiabatic warming over the Dakotas and eastern Montana and Wyoming. And that's definitely working in the favor of keeping us warm, as it turns out. And watch out, this is going to be interesting. Next week is going to be a really interesting week. But we'll talk just about the weekend today. So let's keep on going through our 850 maps. This is now Saturday night, and we've cooled off a little bit, but that's just radiational cooling. It's not because there's any particular change in the advection pattern. It's just the sun's gone down. And notice the high plains stay warm as a consequence, I presume, of that flow across the high terrain. And there's a cyclone that further accentuates that tendency by just pushing the warmer air northward at our latitude, but to our west. Let's keep going. This is really interesting. I don't know, we might do it.
Yeah.
Okay, so that's really warm. That is plus 22 to 24. And the question is, will this cyclone be able to drag that warm air during the day Sunday over us? It's a pretty good distance to get into the heart of that warm air. There's going to be places here in Nebraska and the Dakotas and Kansas that'll be over 80 degrees. I don't know if we'll make it. The temperature advection is not working in our favor. It's not really acting to cool us down very much, but it's not really going to be an advective thing as much as a translational thing. And I don't know if the translation is going to work yet. So let's see if we can get to 18Z, maybe 12 hours from there. See what it looks like midday Sunday. Yeah, unfortunately, the warmth has finally ceased being resupplied by cross-terrain flow, is my guess. And so it's going to get cooler in the high plains. All of that warm air at that high latitude's evaporated, so translation won't even work for us now. Now we're going to have to rely on advection. We're midday Sunday by now. And so if this whole complex could move east, get us into the warm advection again, maybe that warms us up again, but I don't think so. I think the development starts to take root to the south. So let's see if that's right.
Another 12 hours?
Yeah, that's a good idea. But that's fine.
Oops, I'm sorry.
Yeah, so here we are on midnight Sunday, and we've completely, all of that warm air is gone. We haven't changed our temperature very much, but it's not superlatively warm anymore ahead of this evolving cyclone. And look at how the cyclone now, as it begins to take shape, so do the obvious frontal regions. Here's a warm frontal region well to its north and east, and then a pretty strong cold frontal region down toward the Gadsden Purchase area of Arizona, New Mexico. And look at the difluence here, 452. That's differential temperature advection. Really strong warm advection on the warm side, zero temperature advection along this blue contour up here. So that means you're pushing the isotherms together, and you know what you're going to get, thermally direct circulation. So it's going to be raining in southern Ontario and Minnesota, northern Minnesota, in association with that frontogenetic activity. And then you get the same type of activity for different reasons along the cold front. So just for the fun of it, let's look at what midnight on Sunday looks like at sea level and the forecast precipitation. So we get a little bit of forecasted precipitation along that baroclinic zone. It's not all the way up here. It's probably just because this is moisture starved. This has been advected. High water vapor content off the Gulf of Mexico has made it that far north. Some of it gets used up over us by the time we get to midnight Sunday, and then there's a little bit of precipitation on the backside here. A little bit here on the cold frontal region in Kansas, but not all the way down the cold front. So that's an interesting precipitation distribution and a nice development of a cyclone. So it's going to be windy and rainy by the time we get to Sunday night, it looks like. And I guess I'm going to say, let's see what, does Pivotal have those maps of surface 2 meter temperature? Let's see what they say for the final word. I'm going to guess that we don't get above 75, 76 on Sunday. And that'll be earlier in the day than when the clouds come in. And with the threat of clouds coming in, that's even worse. You just take some of that diabatic heating away. So that's not good. And this is Monday night. So let's say Sunday at 3 in the afternoon. So 21's Eve. Yeah, 76 at Rockford, 65 Milwaukee. That's the lake. So for us, 75. Man, we're going to come close, but we're not going to do it. And what I'm going to keep my eye on is, it certainly won't be advection. So if it's windy, it won't matter. But I'm going to keep my eye on the clouds. If the high clouds start to come in as this development to the west starts to ensue, I think we're in trouble for even 75. So this could be an overestimate by a degree or two, maybe more than that. But if the clouds stay away, it's a good bet. Look at how widespread the 80s are. Oh my God. 92 at Omaha. Unbelievable. So it's going to be a warm weekend. But enjoy it. Couldn't be better for homecoming, I guess. So Pete, thanks so much for driving, expert driving, as usual. And thank you all for your attention, and we'll see you next week.